So hello, everybody. My name's Adam Hoover. I'm Surya's professor. I'm his mentor. This is Surya Sharma's PhD defense. He's going to give us a talk that'll take about 45 minutes. And then we will have questions from the general audience. So everybody is free to ask any hard questions you'd like. After we have a general discussion, we excuse the audience other than the committee members so that we can then have a more personal discussion with Surya about his work. Before I let him start on his talk, I just want to say a few comments about Surya. He's been with me for several years now, and Surya is a true old school philosopher. He enjoys not just the coding and the programming and the experiment design, etc. He loves talking and thinking about the big ideas. And I have enjoyed so many discussions with him late into the night about big ideas. I just want to thank you, Surya, for all those conversations. With that said, Surya, whenever you're ready, please go ahead.
Okay, thank you for the introduction. We are here today for my final PhD defense, or maybe not the final one. It's titled Detecting Periods of Eating in Everyday Life by Tracking Wrist Motion, or What is a Meal? Essentially, what we're trying to do is we're trying to build a wristwatch that can detect if people are eating or not eating and do some other cool things with that. I'd like to thank my committee members. Dr. Hoover is the chair, Dr. Dean, Dr. Lau, and Dr. Wang for being here and evaluating my work. To summarize what we will be discussing today, here's a brief outline. We'll start with the motivation for this work. We will consider related work, what other researchers have done. We'll describe a data collection. We'll describe replicating a previous algorithm that someone else created on this new data collection. Briefly, we'll talk about filtering linear acceleration that helped us in improving the performance of this algorithm. And then we'll spend a majority of the time discussing secondary activities, which happen when people eat food in everyday life outside the lab. And we'll discuss CNN that can detect if eating is happening or not eating. And we end it with the conclusion. Most of this work has been either peer-reviewed and is published, or the last one, this section on the CNN, it's been submitted for peer review to JBHI. Okay, so let's get started. Feel free to ask questions. Because I'm going to be talking for 45 minutes, it gets really boring delivering a monologue. So you can type in the chat with a question. If it's too detailed, I'll discuss it after the presentation. If it's quick, I'll try to clarify it at that point of time. So what's the motivation for this work? The primary motivation is the problem of obesity. Both the CDC and the WHO have recognized that obesity is an increasingly larger problem in the population. When I started this research, 33% or 34% of US adults were considered obese. 5 years later, that number has already jumped to 42%. So there's been about an 8% increase just in 5 years. It has been shown that obesity can lead to premature preventable death, which is not good. There are different ways to tackle obesity and achieve weight loss. One is surgery. You can use liposuction to reduce fat from the body. Or the other one is bariatric surgery. So you can actually staple parts of the stomach and it reduces the amount of food you eat. Most people don't like that and prefer lifestyle changes. They'll try to exercise more or they'll try to eat less to achieve weight loss. Personally, these are my photographs from the last 10 years. The first one is from when I was in India. And then the last one is me in the last few months. We've all heard the freshman 20. I did a sort of freshman 40 when I came to America. And this was me at the highest weight of 265 pounds about 4 years ago. That's when I realized that I had to lose weight. I had to do something about it. I got to my lowest weight last year. This is February 2019. And then recently, because of coronavirus, the stress of completing this PhD, I've gained another 20 pounds. The strategy I used was to note how much food I consume. This is on the right, you see a food diary that I took in September last year. I noted how many calories I'm consuming and things like that. As early as 1998, it was shown that self-monitoring what you eat is a vital component for successful weight loss. And most people use food diaries because they're convenient to use. Unfortunately, if you look at my personal use of food diaries, on the right, you see a calendar from June 18 to June 20, and you'll see that I've only used the diary in 4 different instances, maybe less than a week. There has been literature review before and surveys. A survey of 200 users of an app called Eatery showed that only 3% of the users continued using the app for more than a week. So it's really hard to keep using these apps because the burden of noting things is really hard. So the challenge what we want to look at is, can we create a wearable device for eating? We've seen the Fitbit, we've seen other devices that can count how many steps you take. They can count physical exercise, how many calories you're burning. We want to create one for eating. So what have other researchers tried? There are many groups across the world that have been experimenting in this field, and they've tried different kind of sensors. Really early work, so in red you see work from 2010. They realized that you can detect sounds like swallowing or chewing using a microphone, and using these sounds you can detect if someone's eating food or not eating food, or you can count how many times they swallowed food. On the right is another device called the Oracle. That is from 2018, and the reason I put it here is because this is there are 3 researchers from Clemson Computer Science who worked on this device. Dr. Jacob Sorwer, Dr. Kelly Kane, and I believe there's one more. This device is worn behind the head. It contains microphones and motion sensors, and it can also detect if people are eating food. Most of these devices are prototypes and they're proof of concepts, and they're tested on about 5 to 25 participants. So that's earphones. Recently, people have tried necklaces. Necklaces are easy to wear. So some people prefer those. And you can detect if the esophagus is moving, you can detect sounds, you can detect if the jaw is moving while chewing, and you can sort of detect eating with that. Again, these devices are prototypes. They've been tested on about 25 participants or less. Most people wear glasses, so this is actually one of the up-and-coming ideas in the literature. Researchers have started fitting glasses with cameras. So cameras can see food. If they see food, you can tell if that person's eating. You can fit motion sensors. This one's interesting, where it uses EMG sensors to, it tries to detect the motion of your muscles. So you can try this. If you place your fingers around your temple over here and you try to chew food, you can feel that the muscles over here are moving. And these electrodes detect that movement, and they can tell if someone's chewing food or eating food. This work is recent. This is less than 3 months or 4 months old. These glasses have 6 different motion sensors, and they have a camera and I believe 1 other sensor. So it's like the Swiss Army knife of detecting eating, and it contains a host of sensors to detect eating. Again, they've been tested on less than 25 participants. The last one we'll discuss is a wristwatch. Our group has been working with wrist motion for the last 11 or 12 years in various ways. The latest work that was published using a wristwatch was this one right here. I think this is from March. And using commercial watches, they could detect periods of eating. we've done, Dr. Hoover did an experiment on around 2013, they published it. Smartwatches weren't available back then, or the features they had weren't really good enough. So he had to fit people with iPhones on their wrist using an armband and then track data, track motion with that. Why we use the wrist, and the reason we use the wrist is because there are multiple surveys that have shown that wristwatches are preferred compared to the other modalities. So wristwatches are preferred compared to glasses. Not everyone wants to wear glasses. Not everyone wants to wear earphones all day, and some people don't want to wear necklaces. Also, in similar work, we're going to watch a video of someone eating. So when researchers want to create a technology like this, what they end up doing is they end up collecting sensor data, which is on the right, these squiggly lines. And they also need to know when someone is eating, because you need to tell the computer that someone's eating or what they are doing. So you need some kind of method to do that. In this experiment, we put cameras in the ceiling, and we know when this person was eating. So we'll watch a little bit just to get an idea what's going on. You can see that they're wearing a sensor on their right hand, the dominant hand. And as they eat, we'll see the change in sensor data. The three lines are acceleration X, Y, Z, and then rotation X, Y, Z of the wrist. What you'll notice is every time they move their wrist to the mouth to eat food, the squiggly lines get really large, while the other times the squiggly lines are small. So when the hand's not moving, there's not a lot of motion. They'll proceed to pick up the pizza again, so their hand will move down, and then it moves towards the top. And you see that those squiggly lines become bigger again. Dr. Hoover's group has been doing wrist motion tracking for many other things, eating detection, walking tracking, in detecting gestures during eating. So he's developed expertise in this field. Okay, so what did we do? We started with the data collection, and what we wanted to do was we wanted to collect a large data set of wrist motion from participants in everyday life. These participants came from all fields, so they were not just students, they were all across Clemson and the cities of Pendleton or Greenville. And we also wanted to collect this data without burdening these participants with concerns about privacy or behavior. Previous research and survey has shown that if there's a camera pointing at you, people are uncomfortable with their naturalistic behaviors, and they're also concerned about privacy. So to help with that, instead of having a camera, we provided users with this button on the device. When they started eating, they could press the button to mark that they started eating. And when they stopped eating, they could press the button again to mark that they stopped eating. So what was the result of this data collection? It took us about a year to collect the entire data set. We aimed for 500 participants. We ended up with 400 participants recruited total, of which only 351 provided usable data. The total amount of data was 4,600 hours, of which 260 was eating. You're not eating all through the day. You're only eating for about 5% of the day. So this ratio is important to us to provide reasonable detection accuracy and things like that. We tried to balance the weekdays and the weekends, and we also tried to balance the age, gender, ethnicity of the participants, and the BMI. The numbers you see in purple are what the state of South Carolina has. So we got pretty close to what the state has, what the state's demographic numbers are. The only difference is we have a lot of international students at the university. So this was a little skewed, the class with the other student in the other category. So it took us 1 year to collect this data. It took us another year or longer to clean this data, check annotations, make sure it makes sense. The total size of the data set is about 90 GB. 86% of the data was usable. The reasons we lost some of the data were because some users either forgot to turn the device on or they turned it off by mistake. 2 users carried the device in their pockets while recording data. That doesn't give us any wrist motion data, so that's useless to us. We lost 2 devices. One was chewed by a dog, another was lost in the gym. And this shows that this device was comfortable enough to wear in situations where other devices may not be wearable. And about 5% of the data was lost because the hardware crashed. Again, this shows us how often such a device can crash if we deploy it into everyday use. The final result is that dog ate my homework is a valid excuse in any scenario, not just for undergrad or grad students. It works anywhere. What else did we learn? So this is a table that shows other works in wrist-based tracking of eating. It's sorted by the number of meals that were collected. And we collected between 10 to 100 times more data than previous work in this field. So the next step would be to start working with this data. The first thing we wanted to do was try and replicate a previous experiment to see if the data makes sense, just to get a feel of it. So the experiment was done before, published in 2014. They tracked data. They tracked the wrist using an iPhone. We switched to the shimmer. We collected much more data. The shimmer weighs much less than an iPhone 4. So we expected much more variation. We expected much more natural behavior in our participants. Just to summarize what they did, you will see this bottom graph very often throughout these slides. And what we are doing is we are adding the accelerations on the X, Y, and Z axis for the wrist, and we generate this graph. So anytime you see high areas, that's when the wrist is moving a lot. And if you see a low area, that's when the wrist is moving less. This is what it looks like throughout the day. So you start at 7:30 in the morning. This day ends at 7:30 at night. And so this is the wrist motion throughout the day. And then these arrows that point downwards, they showed self-reported periods of eating. What the researchers realized is that usually if you're eating a meal, your wrist moves a lot before and after you eat. And then during the meal, there's sort of this valley of that you can see. You can see it breakfast, you can see it snacks, afternoon snacks, and dinner. This is one of the participants that showed good data. Naturalistic living or everyday life is not as convenient, but when they collected their original data, this pattern was seen very often. From here, what they did was they decided to look at time periods between these mountains or peaks. And then based on that time, they would look at the data and they would decide if this period was eating or not eating. Because we're short on time, I'm going to skip these details as this is not my contribution. This is what it looks in the system that we create in the classifier. Vertical blue lines show self-reported times, and then underscores over here, the blue dashes here, show the detections by the classifier. You see that breakfast and dinner work very well. There's a short lag for lunch, but in general, the method picked up all 3 meals. In terms of numbers, when trying to replicate, we lost about 6 points in accuracy of overall detection. In terms of detecting periods of eating and detecting periods of non-eating, we lost about 10 points in accuracy. We also noticed that the time difference between our detections, so when we started detecting eating compared to the actual start of the meal, or the end of the detection compared to the actual end of the meal, ours was much worse. It was close to 5 minutes, while in the original experiment, it was less than 2 minutes. So based on these numbers, the obvious question for us is that why did replication not work as well as we expected it to? Since there are about 10 participants here, if anyone wants to guess what went wrong, please go ahead and suggest some ideas, and then we will discuss what we learned through this discussion. Okay, I'll keep going. So we first started, we had been staring at graphs like this for a very long time. So our first reaction was, okay, let's look at the sensor data. Our sensors collected linear acceleration, and our research showed that the linear acceleration at the list is actually much, much lower than linear acceleration in other scenarios where accelerometers are used often. Commercial accelerometers are designed to be used in mobile phones, in drones, in cars to test crashes and things like that. The wrist on average during the day is moving at a very low acceleration. And what we learned is that 70% of the noise, that's this blue curve over here, the noise, which is the blue curve, overlaps daily motion by up to 70%. And this can sort of create problems if you're trying to detect activities like eating. We added a simple filter to our system to see how that helps. We got minor improvements. The filtering improved the detection of peaks, which were being used for segmentation. And we got a 2% increase in detecting eating. We got a 1% increase in detecting non-eating. Overall accuracy did not change. So that was a small lesson we learned. We're going to now move on to a major cause of this change in, or this reduction in detection accuracy. We looked at other literature and we realized that a lot of other work has also suffered the same issue. Whenever they take a method that works well and they put it in the hands of real people, they can see a drop in accuracy anywhere between 2 to 40%. And there's other research which showed that behavior in general changes when you deploy a device to everyday life. So let's talk about how people behave, or how what wrist motion looks like when people are eating food. Just go ahead and close your eyes and imagine yourself eating a banana. So if you're eating a banana, the first thing you do is you peel the banana and you take a few bites from the banana. You don't gobble it up. It's like some people gobble it up, but that's not usually how it's done. You take a few bites, then you peel the banana some more, and you take a few bites, and then you're done eating the banana. So you can actually see that in the wrist signals. Again, these are 3 XYZ acceleration signals and then gyroscope or rotation signals. And you can see whenever the signals get a little crazy, that's when they're preparing food. And the action of actually loading or putting the banana into the mouth is pretty clear and can be seen easily. On the other hand, let's look at wrist signals from walking. While it looks crazy, there's also this beautiful pattern to it. You can see lots of tiny up and down movements. And these oscillation are steps. In the interest of time, I'm not going to play the video, but we can watch it after if someone's interested. So if I showed you just sensor data as a human, could you decide which one's eating or which one's walking if I just showed you these 2 images? As a human, you can sort of tell, okay, the one on the left looks like bites, the one on the right looks like walking. Similarly, a computer can use mathematical models and numbers. A computer can look at the frequency of the signal, which is how fast these up and down movements are coming. They can look at the magnitude of the signal, so they can look at how high these signals are. They can compare these 3 signals to the bottom 3, and you can see how this one has more motion than this one. And you can use all these kind of tricks in a mathematical model to tell which activity is which. And that's how most models work. However, what happens is when you deploy it to everyday life, things aren't this separate or this easy anymore. This is wrist motion signal from someone who was walking and eating a banana at the same time. You realize that suddenly it's really hard to see the bites. You can start making guesses, but it's almost impossible for a human and also very difficult for a computer to figure out if this was walking, if this was eating, or what was happening at what point. So we realize that this is one of the key issues that is causing confusion to our method and our algorithm. We looked at the data we had collected while asking our participants questions. About 75% of them said that they were doing something while they were eating food. 25% of those, 25% of the entire cohort said that they were talking, while 50% said they were doing something crazier. How crazy can things get? Well, the obvious ones that most people would do is read a book or watch TV or work on a computer. The ones that can get really hard for a computer are things like putting away groceries, playing with kids, walking your dog, or talking in a car. The motions that come from these activities can get really confusing. So what we decided to do was we decided to build a rest detector, a simple algorithm that can detect rest. All it does is it looks for the variance in the signal. So if there's a lot of flat lines, it says that it's rest. If there's a lot of zero crossings or if there's a lot of up and down motion, you can tell that it's walking and detect walking. However, we needed a data set where we knew what was walking and what was resting. The data we collected only had indications on when people were eating or not eating. For the rest of the time, we did not know what was going on. Thankfully, our group had collected other data before with video evidence. So we had the cafeteria data where we had people eating food in a cafeteria where their wrist would be resting. Similarly, we had a pedometer data. This was collected by Ryan Matfield. It has data from 30 participants who were walking in an uncontrolled environment. They were walking around the University of Clemson, and they performed different activities. So we tested these detectors that we made, the resting and the walking detectors. We tested and we trained and tested them on these two data sets. Once we were satisfied with the performance, we used these detectors on the eating data set. What we learned was that compared to cafeteria meals, humans are resting almost twice as much. So the wrist is resting twice as much during meals. And we also learned that humans are walking up to 5.5% of the time during a meal. In total, approximately 18% of the time of everyday meals is either walking or resting. It's a secondary activity. In the 1,133 meals that we had collected, 21 were shown to us to be predominantly walking. 38 were shown to be predominantly resting, which means a human or a computer would find it very difficult to consider these as eating. After some more analysis, we decided that there were 1,063 meals that we considered valid, and we are releasing these as the Clemson all-day data set. We release all the meals, but our evaluation is going to be on these 1,063. By using these detectors that detected rest and walking and excluding some periods, we were able to improve the classifier accuracy by 3%. Also, we learned that it's a little easier to detect meals where you're just eating rather than meals where you're performing other activities. So this is some analysis and visualization from our experiments. This shows 10-minute and 11-minute meals where the participants were just eating all the time. So each of these blocks is a 1-minute interval. So this is usually what lab experiments would look like. Compared to everyday life, I have many examples, but I'll just pick one in the interest of time. This is a 30-minute meal. That should be the first indicator. Human beings rarely eat for 30 whole minutes. From personal experience, if I ate for 30 minutes in one go, I wouldn't eat food for the rest of the day or the next 2 days, right? So this shows how different everyday living is. Our visualization showed that this person was eating and performing other activities while eating, and they actually, of the 30 minutes, they spent about 1/3 of the time either walking or resting. So what are the lessons we learned from this experiment? We learned that secondary activities happen during majority of the meals. So they are not outliers, they're actually the norm. We learned that lab experiments cannot capture human behavior very well. And the more important ones were that the motion patterns that are created by secondary activities, they impact the detection of eating. And we also learned that these secondary activities happen while you eat and intermittently, which can make it very difficult to model eating activities in general. We're going to take these lessons and we're going to build, we're going to now demonstrate a method that can detect eating activities, and we'll use a CNN to do this. To start with, let's talk about how other researchers have approached this problem. This is as early as 2008, and this is a recent paper from 3 months ago. Researchers will often detect short gestures or short physiological events like a bite or a swallow or a chew. So you can see that these last between 1/2 second to 5 seconds. So in 2008, they were looking at swallows and chews and things like that. The 2020 paper detected movements from the table to the mouth, which is called a bite. And those are these red dots. Whenever during the day they find a large presence of these or a high concentration of these short activities, they look at those periods, they combine them, and they consider them eating. So you can see that here, and then you can see 2 ideas over here. What we wanted to do is a little bit different. We have shown, or previous work by our group has shown that behavior that is outside of eating, so things like meal preparation and cleaning a meal, those peaks at the start and the end of the meal, they can help indicate that someone's eating. Previous work has also shown that activities during eating, like stirring a soup or a drink, or cutting your food and resting between bites, that can also help improve detection accuracy for in-meal gestures. So what we want to do is we want to look at large windows of data rather than just short 1/2 second or 2 second windows. We wanted to look at 6 to 15 minutes of data, and we wanted to see if we could detect eating. So how do we do that? We used a sliding window, so we had a full day of data. This graphic shows you 11:30 to 2 p.m. in the afternoon. You can take a window of data, you can process it using a neural network, and it can give you an instantaneous probability of eating for that moment of time. So we did this for every datum. You can do this for every second, you can do this for every minute. It doesn't affect the accuracy that much. So if you had a model, you could generate this signal. This model would depend on the size of W. So W is a parameter on the size of the window. If you had this signal, you could then use a thresholding mechanism. You could say, okay, if the probability of eating is greater than 80%, that period of time is eating. Instead of using just a single threshold, we use 2 thresholds, a start threshold and an end threshold. The reason for this was that we keep a high start threshold. So the probability of eating has to be really high for us to trigger an eating activity. That reduces false detections. On the other hand, a lower N threshold helps us adjust for the boundary of eating. When you're eating a meal, at the end of the meal, you slow down your eating. You don't eat as fast, you're satiated. So the probability of eating decreases. And this threshold actually helps improve the boundary of detecting eating activities. To summarize, we have 3 parameters that this model depends on: W, start threshold, and N threshold. Okay. So we now discuss the convolutional neural network. It's a pretty simple model. It looks at W minutes of data across 6 axes. There's 3 convolutional layers, and then there's a short dense network, which helps us get the probability of eating. So we're looking at W minutes of data. The first layer is 10 filters that look at data of 3 seconds each. In previous research, we showed that the average wrist motion for a bite is about 3 seconds long. So this filter looks at those motions. The next one looks at consecutive motions, consecutive wrist gestures. So it looks at 2 of them at a time. The rest of the network just helps drop down from this large amount of data to a single number between 0 and 1. If you have any questions, I can discuss more, or we can move on to the next part. Okay. So the question is, how do you train this neural network? And how do you adjust for all these window sizes? We had models for window sizes of 7.5 seconds and up to 15 minutes. We wanted to use 5-fold cross-validation to make sure we are not doing anything wrong, and we aren't underfitting or overfitting the network. So we had a total of 75 different models we trained. We generated windows, W-minute windows from the data set for each model. And we labeled the window as eating if 50% of it was within a self-reported period of eating. If you end up doing that, what you'll realize is that because you eat only 5% of the day, only 5% of the data set is windows that are eating, 95% is non-eating. This can complicate matters for a CNN and many other classifiers. So we undersampled the non-eating class and to balance our data set. And then we use that for training and for testing or validation. So what were the results? I'd like to remind everyone we had 3 parameters: W, start threshold, and N threshold. To evaluate W, we looked at the accuracy of classifying windows of data. So a window was labeled eating or not eating, and this is the accuracy on that. What you notice is that as the window size gets bigger, it actually becomes much easier to detect eating. On the other hand, as the window size gets bigger, it takes much longer to compute the process on these windows. It takes longer to predict, it takes longer to train. So we settled on a window size of 6 minutes for this reason. So that's the effect of window size. We also wanted to look at the effect of start threshold. So in this plot, you see TPR, which is the percentage of meals that were detected correctly in the data set. And on the x-axis, you see false positives triggered per true positive. If you detect too many false positives, people lose faith in your system. It has this sort of a cry wolf effect. So we have to balance both good detection of meals and the false positives that we see. We picked the start threshold of 0.8. You see a knee over here, and we thought it balanced TPR and false positives pretty well. So after picking the window size W and the start threshold TS, the last one is the N threshold. Again, instead of the true positive rate this time, which wasn't affected as much, we put the boundary error here. If you make your window size really big, like 30 minutes, you can detect a lot of eating, but the precision of which you will detect these eating activities is going to be bad because your boundary is going to be bad. So in this graph, we picked 0.4 as the end threshold. It balances FPTP to a boundary error of about 1.2. And we thought that was satisfactory for this algorithm. So how well does our algorithm do? Compared to the Bayesian algorithm on the 1063 meals that we have, it detects the same amount of meals or a similar amount of meals, but it drops false positives by 67%, which is a huge improvement. Compared to the original experiment done 8 years ago, we detect 3% more meals on a much more bigger data set, a much more data set with more variation. And we also reduce the false positives by about half. So this final method does much better. We're showing other work in risk-based tracking and detection of meals for comparison. It's hard to compare work really because our data set is much bigger and a lot of work has not reported some of these numbers. It's possible that in other work, all the meals were detected, so they didn't consider it important to report these numbers. What we are showing is that if you started looking at large data from everyday living, you are going to miss meals and you are going to trigger false positives. In terms of time metrics, so if you label each datum of the day as correct or incorrect, our CNN performs better than the Bayesian method. You get a 25% increase in the F1 score. You get a 6% increase in the weighted accuracy. Again, it's hard to compare with other work. We are showing it for completeness. Some of these metrics are affected either by the imbalance in the data set, which is the ratio of eating to non-eating, or they're affected by the size of the data set. And we can discuss this later if there's interest in understanding this. So this is a home stretch, I guess. What did we learn through the last few years of research? One, we are showing that there is evidence that non-eating actions and non-eating behavior during meals can be indicative of eating. There is other research that has shown this. There has been research where a wristwatch on the non-dominant hand was used, and it could also detect eating. So you're eating with the right hand, on the left hand, and the left hand can show evidence that there's eating. We are doing something similar, but we are talking about other behavior in general. We showed that using a large window of say 10 or 15 minutes can improve the classification accuracy of detecting those windows by up to 15% compared to using short windows. We are showing that top-down approaches compared to gesture spotting or bottom-up approaches should be explored. Maybe you can combine both to get better improvement in detection. One of the conclusions that we noticed was because of secondary activities, it's actually very hard to detect 100% of the meal correctly because the data itself is a little confusing. And lastly, what we'd like to note is that our field is still so new that comparisons between different works on different data sets should be made very cautiously without assuming that these metrics will transfer from one data set to another. That's all I have. I'd like to thank everyone for attending. This work was supported by NIH for 3 to 4 years, and I'm really thankful since they paid for all my food on the table and all my other fun stuff. We will now open for questioning.
Thank you, Surya. That's a great talk. Questions from the non-committee members. General audience, if you'd like to ask Surya anything, please go ahead.
Hey, Surya. So when you're choosing the start threshold probability, you were talking about using a window size of 6.
Correct.
So does that depend on the window size? Like if you use a window size of 8, would the start threshold be different, or did you do a comparative study?
So we did a grid search. We looked at everything. I looked at 18,000 different combinations. It does depend, so these combinations matter, but to summarize the results, these are the best. This one combination was the best we saw.
So while choosing the window size, you were also playing around with different start threshold probabilities.
Right.
So you didn't do them independently.
Yeah.
Okay. Yeah.
Hey, Surya. Could you please elaborate on the non-dominant hand usage or detection? Because you said something about that in your conclusions.
Right. So we haven't done that, but there was at one paper 5 years ago that did that. I thought it was very interesting that there are patterns of the non-dominant hand that can lead to conclusions about what the other hand is doing. I don't have the details. That was not my work. It's been 5 years. I just pointed that out because it's similar to what we are showing, that that non-eating activities can hint about eating activities.
So your algorithm is heavily dependent on the person wearing the sensor or the watch on their dominant hand. Or
Correct.
I guess it depends. There's another level of variability there, because some people might not like to wear the sensor on their dominant hand, but they might use it for eating.
Correct. That is correct. This is partly between research device to all the way. So we are working on these ideas. It's a limitation of our work. Yeah.
Thank you.
I think we have a question from the YouTube stream. How are we storing data on the device? So the data on the device is stored by on an SD card. So it has a battery that can run for about 48 hours or more. So wrist motion data it's not a lot of data. I think an entire day of data can be stored with clever compression tricks and other in like 8 or 9 MB of data. So it's not a lot.
Hey, Surya.
Hey.
What would be your next, if you had to improve this, what would be your next step? Which area do you think is more promising? Machine learning part or integrating some signal processing concepts into the current algorithm?
One of the reasons, Dr. Hoover has sort of drilled into me that I shouldn't be sharing future work because we have 3 or 4 other ideas and our master students will be working on them. But in general, everything is promising. Filtering, segmentation, and the classifier itself, all 3 have demonstrated that there are things that can change and help improve things, and then there are evidence that something might never improve. When 3 years ago, I had a document containing between 7 or 8 different ideas. We had hand-selected features that we were looking at. So it's really hard to tell which one of those might help improve accuracy at this point of time.
Mm-hmm.
You can talk about the context, Surya. What we need is better ground truth.
Yes. So yeah, we need better ground truth. So one of the issues where we let our participants press the button to decide when to tell us when they started eating or when they stopped eating, and this button press is a part of human behavior where people might forget and start walking. So the actual labels that we have might be incorrect. What's interesting is that the CNN can work around that and detect eating to a satisfactory level. How do you differentiate between drinking and eating? So we did not collect that data, so it's very hard. There are other groups that work specifically on detecting drinking. When we collected the data, we gave a specific definition on what a meal is. So we said the primary activity has to be eating or drinking for a substantial amount of time. So if you're grazing while working on a computer, if you're just chewing peanuts or something while working on a computer, or if you're eating popcorn in a movie, tell us that so that we know how to work with this data. if I had to guess on how you could differentiate between drinking and eating, this is a glass. The wrist moves in a very different manner if you look at my right wrist when I'm drinking water. So the range of this motion is very limited. When you're eating food, so it goes like this and does this. If you're eating, the range of motion gets much more crazier, using both your hands. Sometimes you're using a fork, knife, and things like that. So all these small differences can help you differentiate between them. I think one of our previous researchers looked at that. Yiru could detect between eating and drinking in her research. Yeah.
Hey Surya, Purna here. So you spoke about the different window sizes.
It's another chat question.
I did the chat questions. Let me check if there are any more. But
There's one more talking
more?
about the ratio of data.
it's the total hours of data collected or duration. Let me understand this question. Okay, so
The ratio of eating to non-eating. I think that's
Right.
the question. Explain that a little more.
okay, so when you're building classifiers, classifiers work much better if all the classes contain equal amounts of data. We have a issue where the data we collect during the day, 95% of the time is not eating, and only 5% of the time is eating. So the classifiers get confused. They don't work very well on this. So when we collected our data, we collected a full day of eating. So we got this ratio of 20, that non-eating data was 20 times compared to eating data. When you're doing lab experiments, you might have people come eat food for 10 minutes, and then you might ask them to run for 10 minutes. You might ask them to work on a computer for 10 minutes. And that creates a one-to-one balance between all these activities, which can make detection easier. And I hope that answers the question.
Hi Surya, Purna here.
Hey.
Hi. So you spoke about the different window sizes. So the output of the CNN, it's always the precision of the start and end is always in terms of window sizes, right?
Correct. So you have to look at a fixed amount of data when you're feeding it to the CNN.
Right. And you said larger window sizes give you, like, you can detect it. You can't detect the start point and the end point well, but you would
Right.
almost always detect eating period. So
Right.
I was just thinking, did you try like a larger window size, but then look at this the first window size and the last window size, and go inside and vary the window sizes there, or something more complex? Something that is often done in like speech recognition and
Right,
speaker
right.
identification model.
That is an idea, and I know Dr. Who is writing it down, because we've been so this was an idea we've been discussing before we started the CNN,
Right.
on looking at different sizes of windows. We had to decide what the scope of this research is going to be, so we decided to end it here. We didn't look at those like fine-grained sizes for windows.
Yeah, I understand. Yeah, thanks.
Okay. If there are no more questions, I will end this stream so that we can have the closed session now.
Last chance for general audience questions. Thank you for all these good questions, by the way. We'll give it an extra 15 seconds, Surya, in case people are typing.
We did get a message from our 6-year-old nephew. His name is Surya Sharma. And all he wants to say is that he's just fascinated with everything Surya, his uncle, is saying, and he really wants to start doing this himself. 6 years old.
Never too young for graduate school.
Yeah, and he's actually doing coding. Like, he's learning very basic coding. So this is just fascinating him.
Very nice. Surya, you're inspiring people around the world. Okay, everybody who's not on the committee, thank you for coming and listening to Surya's presentation. I hope you enjoyed it. Please drop out. Now it's an opportunity for the committee to have a deeper discussion.